Well, thank you very much for having me here and for attending this seminar. I know it's a bit difficult sometimes having Zoom talks, but anyways, I think this WOST thing is working quite well for several years, so it's great to be here. Today I'm going to tell you a little bit about some work that I'm doing with a postdoc in my group called Felix Benoit, and it's work that is not published. It's not on archive, so it's quite preliminary still. So if you have feedback, comments, I'm happy to take them. This is the first time I present it. And this work has to do with combinatorial encoding of assemblies and how we can encode them as kinetic traps, right? So I'm going to be using as an example assemblies of letters, right? So I thought it's nice to have this historical construct of the Seto-Rotas piece in which you have combinatorial reusage of letters, right? So you only have 8 letters, but you manage to assemble 5 different words with 5 letters each at the cost of a lot of symmetries. But perhaps a more pertinent example, still a bit playful, has to do with the game of Tangram. Right, so when you play the game of Tangram, I think probably most of you have played it. Right, it's a game you play with 7 pieces, with 7 shapes, and the fun of the game is trying to combinatorially arrange these pieces such that you can construct different shapes to which you give some semantic meaning. Right, so for example, here you have a cat, a duck, and a rabbit. And what you don't want to do is create chimeras like a rabak here, right? So therein lies your selectivity as a person working in the living room on a rainy day to find where to put each pieces, avoiding this type of things, right? And I think a similar paradigm we can see at the subcellular scale, where you have a large number of proteins, each one with its own structure, with its shape, that can assemble into and should assemble into particularly functional protein complexes, multi-component assemblies, while avoiding others that, although to the eye may seem correct, are in fact completely made up, right?
My attempt.
Is there a comment? Oh no, maybe somebody forgot the mic. That's okay. Okay, so this is more or less the paradigm that I want to use, and very briefly I will just say one more thing about protein assemblies, right? I mean, it's complicated, it's regulated, and it's very far from equilibrium, right? So if you look at the self-assembly of protein complexes inside the cells, protein complexes such as the ribosome, you will see that often they entail many different protein species, right? So you can have, for example, in the case of the ribosome, on the order of 100 protein species in a very crowded, highly heterogeneous cytoplasm that will have thousands of different proteins, right? So there's a huge selectivity task to find the correct binding partners in this mixed and in this highly heterogeneous mixture. But this task is solved very accurately and also very fast. Right? So for example, the ribosome within the cell assembles in the order of a minute, right? Despite having very large number of components. And I mean, these schematics here of the assembly of the small subunit and large subunit with the ribosome, they're not meant to just sort of there for visual effect. And so you see how complicated this actually is. Okay, so this is what I will say about cellular protein assembly, and I'm just going to shift towards some more theoretical considerations. So I would like to make a distinction before we go any further between 2 types of self-assembly processes, both of which are capable of, let's say, informally assembling information, right? And one is templative and the other is non-templative. Now, of course, I put a sharp divide. I'm sure that somebody much smarter than me will find an interface between these two. But in this simple case, let's consider the following scenario for templated assembly, right? So say you want to assemble a semantic word, the name of a writer like Neruda. And the way you do that in templated assembly is like you have a tape, a template, which has the words Neruda, and one by one, you will be putting the correct letters by comparing to the template, right? And this is normally done by some kind of, you abstract this into some machine, some protein machine that will carry forward this task. And in this manner, you will generate, you will generate information in the form of correlations between the copy and the template. And if you want to generate a new, let's say, new meaning, a new semantics, right? Well, you just need to have a second template, right? So, for example, if you're French, maybe you want to talk about Proust, right? So then you need to have a new template with the word Proust, and then you will copy it into the copy string. And of course, you can make errors, right? Sometimes you will put the wrong letter. And loosely speaking, you can expect these errors to be somewhat uncorrelated. I'm sure there's, in cellular scale to some level, there are correlations, but what I mean by this is that if you move many bases away from the error, you'll still have the template to pull you down to the correct base to put, right? So errors would largely be uncorrelated, and that would be due to thermal origins. So it would be fluctuations that make you bind the wrong thing. In contrast to this, in non-templated assembly, the idea is that the information of these different structures is already, these different names is already in the mixture. And all you have to do is retrieve it by giving it a small cue, for example, in the form of a seed, right? So if you want to assemble the word Neruda, you just put NE and you expect the rest to grow. And if you want to assemble the word Proust, you put the letters PR and you expect this to continue growing, right? And you will also have errors here, but in this case, you can expect the errors to exhibit stronger correlations in the sense that if you make 5 mistakes in a row, you can expect that the next base that you add has, very, very little to information since it will interact with the nearby bases, right? To know what is the correct component to add. And here the errors there will be thermal errors as well, but there will also be of a different origin, more combinatorial, arising from the fact that some letters will appear many times. As for example, the letter R here appears in Neruda and Proust, so you don't know very well where to put it. Okay, and this is the second type of self-assembly process that I want to talk about today. Okay, so I'm not going to talk about templated assembly. I'm going to talk about non-templated assemblies. It's fundamentally different. I just wanted to make that distinction. Okay, so how do we go from here? How do we establish some kind of a framework to talk about this problem? We're gonna devise a very simple setup, okay? And with this simple setup, I want to convince you that when you try to do combinatorial encoding of, for example, names of writers using letters, this will result in an enhanced promiscuity of the components. Okay, so first let's see what this setup is. So we consider a mixture of components with n-tot components, which can be the letters of the alphabet, but of course can be something bigger or smaller, right? For simplicity, we're going to fix all of these components at the same chemical potential mu. And our goal is to take these components, take this mixture of components at fixed chemical potential, and have it self-assemble into different names, right? So Neruda, Proust, or Marias, a very famous Spanish writer that passed away recently. And we have capital K different target structures, and each one will have a certain size, M in this case is 6, and a certain number of components, right? Different components. For example, Neruda and Proust have each 6 different components. Marias has 5 because the letter A is repeated. And as you try to assemble more structures and bigger structures, you will start making a combinatorial usage of the alphabet, right? That's why we have dictionaries. And for example, the letter R will appear several times in different targets, and the letter A appears in different targets, but also several times in the same targets, right? And what this will result is in an increased promiscuity of the components. So the components are promiscuous in the sense that they can appear in many places, and the degree of this promiscuity, which I'm just going to call pi, depends on the size of the structures, how many components per structure there are, the size of the alphabet, and how many total target structures there are, right? So there's some function of that. And the question that we want to ask is, how can we encode targets in the mixture so that they're retrieved, assembled very fast, right? Okay, so the first idea you may have is encoding structures as energy minima. So you have some kind of high-dimensional assembly space here represented by one dimension. And in this high-dimensional assembly space, you will have some free energy. And this free energy, you can aim at programming, encoding in the minima of the free energy landscape, the particular target structures, the particular names, right? So for example, here Neruda is there, Proust is there, right? Then you will have some kind of disassembled vapor phase, which you can penalize by the chemical potential. And then you can add a discrimination energy, E, such that these chimeric structures are half one structure, half another, half one target, half another, they have they correspond to minima, but to higher minima, right? So you can have this idea. This is a nice idea, and you can then define binding rates Kij plus and minus of addition and removing of component I in the presence of component J, right? With a certain rule that reflects its energy landscape. And the rule would be something like this. Now you just say that there's a binding energy mu plus E if I and J are neighbors in some target and mu otherwise. Okay, so if you do this, what you should expect is that for low values of the chemical potential, there will be a slow relaxation towards the energy minima. And for large values of the discrimination energy, the energy minima with the correct structures will be very deep. And so this will result in energy minima encoding, right? Which will be accurate. That will be accurate when the assembly process is very slow. Okay. So we can test this idea, and I should say this is not new to this project. Right? I'm just sort of explaining it to you. But this was an idea originally proposed by Stan Leibler about maybe 8 years ago, and that I worked on with him during my postdoc. Okay, so let's test it, right? When the assembly is very easy, we have a seed, which can be, for example, the word zebra, and we have a target, which is the zebras jump quickly, which happens to only use each letter once. And over time, what you expect is that, that this polymer grows and assembles this information, right? Which you've encoded in the binding energy of the components. Okay, you can do actual real simulations of this. And indeed, this will give you a very accurate assembly when the chemical potentials of the order are very similar to the binding energy. But this assembly process will be quite slow. If you want to speed it up by increasing the chemical potential, what will happen is that you have a disordered assembly. And essentially, you start growing very fast. So in this case, you can see that the width below is much higher to the right than to the left, but it contains no information. So we need to think of a new way to be able to encode information out of that can be retrieved fast and out of equilibrium. Okay, so how can we? So the idea that we're putting forward is to try to encode it as a kinetic trap, and in some sense try to not program the mixture through the energy minima, but programming the whole kinetic pathway. And although this sounds very complicated, it's much easier than what it sounds, right? So imagine, now I'm going to use a two-dimensional assembly because I didn't have space in the slide to do with a linear assembly. So imagine you start with the letter WA. So you can bind the letter I to the top or the letter S, right? And you can bias both of these events with a chemical potential, right? So you can favor the assembled state, but we will not discriminate based on the energy difference. Okay, we simply will ask that the thick lines are faster than the dashed lines. Okay, and in this way, little by little, we can favor one pathway over another. Okay, and little by little reach Hemingway, right? So you can assemble Hemingway, not giving it higher energy, higher depth, deeper depth to the free energy minima, but simply making the pathway faster. Now, how do we do that in terms of kinetic rates? It's very simple. You just say Kij over Kij plus over minus, right? Addition is just exponential of mu, right? So there's no discrimination energy, but the Kij plus or minus, right? So the correct pathway, forward or backward, it's just faster, right? So those kinetics are just faster. So and you bias that with some kinetic, some depletion of the very high delta. So if you have that, what you can expect is that at large values of the chemical potential, you will have a fast driving through certain paths, right? And at the same time, if the delta, if this discrimination difference is sufficiently large, the correct path is the fastest. And so what you can expect is that the kinetic trap encoding is accurate when it's fast. Okay, so essentially the opposite of this energy minima encoding. Okay. So this is, again, just an idea. We can test it with simple numerical simulations. And what you find is that for low values of the phenomenology is quite rich, right? You try to encode one assembly, the zebras jump quickly or whatever, right? And for low values of the chemical potential, you have a vapor phase, a disassembly phase, as you would expect. And then when mu is approximately equal to the binding energy, which in this case is 0, what you will have is this assembly and then a growth of a disordered phase, right? So the equilibrium state is just random. Then if mu is very large, but the discrimination energy is lower than some critical, the discrimination barrier is lower than a critical value that happens to also be log n. Then what you have is kinetic, is a fast growth of disorder, whereas you have kinetic disorder, a bit like in the equilibrium case. And then finally, if mu is large, but and the discrimination is larger than some critical value, then you will have a very fast retrieval of an ordered structure, which will, now it doesn't correspond to energy minima, so it will exist for a certain period of time and eventually will be destabilized, right? And of course, the trick is seeing if there's a timescale separation between the speed of retrieval and how long this structure is present there, right? And so essentially, this is the idea that we're trying to put forward, right? That you can encode information in a kinetic in an assembly pathway, and that this information can be decoded accurately and very fast. Okay, so I'm just going to show you a couple couple more things, and then we will be done. Okay, so far I've just showed you how to encode one assembly, right? So and the idea is to encode the whole assembly pathway. So such that from a simple cues such as the letters N, E, you can nucleate the whole structure, such as the word Neruda. And of course, you can do this for other structures in this high-dimensional assembly space. Right? So you can include from IA, you will be able to retrieve Marias, and from ST, you should be able to retrieve Proust, and so on. But you can imagine that if you keep on playing this combinatorial game, as I mentioned, the promiscuity of the components will go high, and eventually you will have some phase transition to a regime in which these pathways cross each other, and as they cross each other, you will go from one assembly to another, and then you will start nucleating this like the rabbit and duck, the Rabak or Nerust or Pruda or whatever, right? This chimeric structures that are deleterious, right? They're not what we wanted. So essentially, we can test this numerically as well. And the idea here is if the number of targets encoded is small, is below some critical value, say just Kc, then this approach should work, right? So you should be able to grow one structure and keep it stable for a certain period of time. But as you increase the number of structures that your mixture encodes, then you will end up in a disorder regime where you form this chimeric structure, such that you start nucleating one structure, then you nucleate a little chunk of another, then a little chunk of another, another chunk of another, and so on. Okay. So now, of course, the question is, to what extent can we do this combinatorial usage of components, right? So what is the coding capacity, right? So I showed you that numerically it seems that we can encode through kinetic traps multiple assembly pathways in a mixture, that this allows retrieval of this information far from equilibrium and therefore very fast, but we don't know what is the coding capacity. I'm just going to give you a flavor. I mean, there's a very simple scaling argument that you can do to understand this. I'm just going to give you a flavor of how you go about it. The idea is that when you talk about kinetic encoding, you should not, it's something that works very irreversibly. Because it's very irreversible, you should not allow any mistake to happen, because you will never be able to remove these mistakes. This is unlike when you have an energetic encoding in which you can reverse mistakes as you thermalize. So here, no mistake can happen. And so the probability that an assembly is formed correctly is 1 minus the error rate to the power of the assembly size. And what you want is that this is of order 1. Okay? So now the whole business is finding what is this error rate, P error, I call it there. And you can show, it's not too hard to show that it scales as a promiscuity over the number of components in the structure to the power of little n minus 1. Okay, so what is this? What are these components? Well, the promiscuity you should expect, right? It's with how many different components each component interacts, right? And this will depend on the assembly size, on the number of structures, on the total alphabet size, and on how many different components each assembly has, right? And we can obtain basic simple scalings for the promiscuity. And then the number of neighbors is with how many partners in the geometry of your assembly each component interacts. So in this simple linear assembly, it's n equals 1. If you have next near neighbor interaction, then you would have n equals 2. If you have a 2D assembly instead of 1, you will have also n equals 2. If you have 3, hexagonal, you can have n equals 3. And so what you obtain in the end is that there's a relationship between the how many. So by putting P(R) in the assembly probability equating to 1 and calculating the scaling behavior of this, you will have a relationship between how many structures you can have, which is some measure of coding, the size of these structures, and some measure of geometry reflected by this exponent alpha. And this exponent alpha is given by 1 over n minus 1. Okay, and we can, just to say goodbye, look at two particular cases. So first of all, is n equals 1, this diverges, right? So essentially, this means that when you have simple near-neighbor interaction in one dimension, you can only encode one assembly. For n equals 2, the scaling vanishes, which means it allows reusability, but it's not extensive, right? So it doesn't allow for any combinatorial explosion of the reusability of components. So it's a finite, some finite size effect, essentially. And as n goes larger than 2, you can have a combinatorial increase of the coding capacity with the system size. Okay, so that was all that I wanted to tell you about. Okay, so this should be more or less the summary image. In brief, I just tried to convince you that encoding assemblies can be done through kinetic pathways, not only by sculpting an energy minima. I think this is a general idea, right? So normally in neural networks, classic work in Hopfield networks, and so on, we tend to sculpt energy minima. What I'm telling you is, out of equilibrium, you can also sculpt energy pathways, right? Kinetic pathways, sorry. There's a price to pay, right? And one price is in form of the dissipation. So this is fundamentally far from equilibrium. I mean, I didn't compute all the usual business of entropy production rate and so on. One can do it, right? And this would be a very far from equilibrium system. And there's another caveat, which is the coding capacity. So essentially, the scaling that I show you is slightly better if you encode energy minima than if you encode kinetic pathways. The future work, it's quite clear for us, is moving towards 2D assemblies. We're already working on this, and it gives a very rich phenomenology. The arguments are a bit more subtle, but the basic ideas hold. And that's all I wanted to say. So if you have any questions, I'll be happy to try to answer. Thank you.